This is section 5.5, exponential logarithmic models. So this is part 2. And this is having to do with radioactive decay. So when you have something like that's radioactive, then we have something called a half-life, which means that if you have like 100 grams of that material, there's a certain amount of time that goes by, that's called its half-life, that it'll go from being 100 grams down to 50 grams. And then when that same period of time passes again, it will drop down from 50 grams to 25 grams. And then the same amount of time, it will drop down to 12.5 grams. So it's always going down to half of what it was before. That's why it's called a half-life. So in this particular problem, the half-life is 1,599 years. It could be any number. And so what I'm going to show you is, first of all, how to figure out what the K value is. Because what we have here for this formula is this Y is basically the current amount. It's hard to see that. This part is the initial amount. And then we've got this constant. This is the constant that we have to figure out. And then T is the amount of time in years. So the key to these problems is we're always going to have the same formula. And you're going to have, if you know the initial amount, you put it in here for C. If you know the current amount after a certain amount of time, that's what's going to go here for Y. The amount of time that goes by in years, that's what you put in for T. But we've got this K, this constant that you have in here, and that all depends on the number of years that have gone by. So, what I want to show you is how you find that K value. Because once you find it one time, you actually can just go straight to the answer. But I need you to understand what it actually means. So, if you have that formula, Y equals C times E to the KT power. We're talking about a half-life. So what we put in here is, I'm going to put in the amount of years for the half-life. So in this case, it's 1,599. Another problem, it might be like 12,000 or 150 years or something like that. So that number, that's the part that's going to change at different times. Now, if it's a half-life, what that means is whatever you start with here, you're going to end up with half of it after 1,599 years. So you could just pick some numbers, actually. So let's just say I start off with 500 grams of something. After 1,599 years, that being the half-life, that means I'd go from 500 to 250. It doesn't really matter what numbers you pick here, because here's what this is going to look like. 250 equals 500 times E to the 1,599K power. I want to solve for K. That's the whole idea here, is that when you're given a problem like this, they're not going to tell you K, but you will be able to immediately write down what K is equal to based off what I'm about ready to show you here. So the next step is to divide by 500, because I want to get this thing by itself. So this ends up being 1/2 equals E to the 1,599 times K power. So notice, this will always be 1/2 here. Because if I had started off with 100 grams, then this would be 50. And when I divide it, it'd still come out to be 1/2. I could start off with 1,000,000 grams. And then I'd have 500,000 grams for the half-life. And so it would divide to be 1/2. So every time it's going to come out to be 1/2, no matter what you start with. Because that's what a half-life is. Now, I want to get to that K. So what we learned is that if you want to get to that exponent, you can get to that exponent, 1,599K, by taking the log with this base. So it'd be the natural log base E, natural log, of this number that's on this side. So to get K, I have to divide by 1,599. That's my K value. So when I'm doing a problem like this, you could go through all this work here to find your k value every time if you want. But there's no need. As soon as I see this, I know that this tells me that my k value is 1,000, the natural log of 1/2 divided by 1,599. So k is equal to the natural log, it's the half-life, that's why it's got the half there, so if you want to put 0.5 there, you can. And then divided by the number of years that is in your half-life. So that's very important because you're going to look at one of these problems. If you haven't paid attention to this, you're going to look at one of these problems and you're going to be like, I don't know how to do this. I don't know what k is. This is assuming that you know how to find k. And it is as simple as that. So if this was like 3,000 years here, k would be equal to the natural log of 1/2 over 3,000. And it really is that simple. Okay, so now I can actually start answering the questions because now instead of having this formula the way it is written here, this formula is now y equals c times e to the natural log of 1/2 divided by 1599 times t power. That's my new formula. Now I know what the k value is. So here, I'm starting off with 10 grams, so that's c. Wants to know how much will be left after 1,000 years, that's t. So I'm going to substitute those in to this formula right here. So y equals, and I had 10 grams to start with, times e, and then it's going to be the natural log of 1/2 over 1599 times t, which is 1,000. So this one, it's just very straightforward. You're going to grab your calculator and you're going to type this all in, but make sure you put this whole numerator or this whole exponent into its own set of parentheses. And so when you do that, that y value turns out to be about 6.48 grams. Now moving on to the second one. So now this one says find the initial quantity. So that means I'm looking for C. I don't know C this time. It says there are 2 grams after 1,000 years. So that means this is my Y and this is T. So again, I know Y, I know T, and I know the K value because I have that in there. The only thing I'm missing is C. So that's how I'm going to set up this problem. So I'm going to have 2 equals, and I'm looking for C, times E, and then this is the natural log of 1/2 divided by 1599 times 1,000. So you're going to have to divide by all of this. So C is going to equal 2 divided by, and so then you've got, down here you've got E to the natural log of 1/2 over 1599 times 1,000. So make sure you put all of this in its own set of parentheses when you do that in that denominator. And so then you will get an approximate value. And this time, if you're punching this into your calculator correctly, it should come out to be about 3.09 grams. Okay, so moving on to the last one. Now it says, how long would it take, that's time, so I don't know time, to go from 10 grams, that's the initial amount, to 4 grams, that's the Y value. So we're going from 10 to 4, probably going to run out of room down here, so let me move over to this page. So I have Y equals C times E to the natural log of 1/2 over 1599 times T. But this time I'm going from 10 grams, so this is 10, to 4 grams. So 4 equals 10 times E to the natural log of 1/2 over 1599 times T. So I want to get this by itself. So I'm going to divide by 10. So So that comes out to be 0.4 or 4/10 equals e to the natural log of 1/2 over 1599 times t. So again, this is a problem where my variable is up in an exponent. So I can take that exponent, natural log of 1/2 over 1599 times t, and set it equal to log base with this base, so that'd be natural log base e, natural log of 0.4. So I want to get t by itself. So now that I have that out of the exponent, I can multiply by the reciprocal of this. So that'd be 1599 over the natural log of 1/2. So multiply this by 1599 over the natural log of 1/2, or 0.5 if you prefer. Just make sure that when you put this in your calculator, this entire numerator is in its own set of parentheses, and then divide by the natural log of 0.5. And you'll get t is, in this case, approximately 2,114 years. I just rounded to the nearest year.